Okay, so let's work this Atwood machine problem here. And so basically we have a mass of 3 kilograms here and a mass of 1 kilogram. So we know what's going to happen. M2 is going to fall down and M1 is going to go up because they're connected by this rope. So it's going to be sort of this type of motion. And so what we're going to do then is define the positive direction is running along that direction of motion. Okay? So therefore for M1, the positive direction is up, and for M2, the positive direction is down. We're just defining the positive direction as the direction the whole system accelerates. So it's kind of, M1's moving up, M2's down. So that's our positive direction for each of those masses. And to solve this problem, really the easiest way, I think, since we're asked about the tension, one idea is to make this whole thing be your system, okay? To have your system basically include the mass, string, and then mass 2. And that can let you solve for the acceleration, but not the tension, because tension would be an internal force to that system. So I think the best way to do this problem is to pick one system as this guy, okay? And your second system is that guy. Okay? So let's identify the forces acting on each system. So first for M1, well, there's always gravity, M1G, pulling down. Now, the tension in the rope, well, the tension is pulling on this system upward. So there's the tension. Now for M2, well, there's always gravity again. There's our M2G. And there's tension in the rope. And since this rope is basically connected to itself, that means that the tension is the exact same at every point in the rope. And the rope has no mass. So that's the type of thing that happens when you have this idealized situation of a massless rope, and there's no friction in the pulley here either. Okay? So what that means is this tension here, the tension that's pulling upward on M2, is the same as this tension over here. Okay? So there's the setup to our problem. Now, our systems are simple enough that I'm not going to draw a free body diagram for each one. There's basically only 2 forces acting on each mass. So what we need to do is apply Newton's second law. The sum of our forces is mass times acceleration to each of these systems here. Okay? Keeping in mind what is the positive direction. Because our acceleration for this situation is upward, and the acceleration over here is downward. So that's what we're trying to solve is the acceleration and the tension. So applying this to M1, applying Newton's second law to M1, our positive direction is up. So the sum of our forces, well, we have one upward force. That's a positive force, so that's tension. Now, M1G points in the negative direction, so we get a minus M1G for that force. So there's our net force, tension minus M1G. And that equals mass times acceleration. And it's the mass of the system. And this system is only M1, so it's M1 times the acceleration. Now, doing the same for M2, we have, first of all, remember for M2, downward is our positive direction. Okay? So therefore, we have our tension, which is pushing up, pulling up. It's in the negative direction because we've defined downward as positive. Downward is the direction of acceleration. So that's a negative tension in our net force. So it's negative T. Now, what about this guy? Well, m2g points downward, and we've defined that as our positive direction. So that's plus m2g. And that equals the mass of our system, which is m2, because our system only encompasses m2, times acceleration. Okay? So basically we have here two equations with two unknowns. Our two unknowns are tension and acceleration. So let's first solve for acceleration. Okay, so let's add this equation to this equation. So when you add these two equations, tension plus negative tension is 0. And we get negative m1g plus m2g, which is m2 minus m1g. And that equals this plus this. And these accelerations, remember, are the same for each mass. Okay, because they're connected by a rope. The length of the rope isn't changing. So if this guy's accelerating downward at 1 meter per second squared, this guy's going up at 1 meter per second squared. So that's why these a's are the same here. So that gives us m1 plus m2 times a. So our acceleration is then, dividing both sides by m1 plus m2, it's m2 minus m1 over m2 plus m1 g. Okay? So we plug these numbers in. M2 is 3 kilograms, remember? So m1 is 1 kilogram. M2 is 3 kilograms. So we get 3 minus 1 is 2. 3 plus 1 is 4. So we get 2 divided by 4 times g. So half of g, basically. It gives you the answer 4.9 meters per second squared for the acceleration. Okay? Now, what we can do then is just plug that back in to equation 1 here and solve for tension. So equation 1, if we add m1g to both sides, we get T is m1g plus m1a. Okay. So m1 is 1, g is 9.8, plus m1, which is 1, times acceleration, which is 4.9. And that gives you the answer, 14.7 newtons is the tension. Okay? So let's look at that. Let's kind of put some of these numbers onto our diagram here. So let me erase some of this here. I'll leave our tension of 14.7 newtons. So first of all, what is m1g? What is the number there? Well, m1 is 1, g is 9.8. So this value is 9.8 newtons. Okay. Now what is m2g? Well, that's m2 is 3, g is 9.8. So that gives you the number 29.6 newtons for that guy, for m2g. And we just found out the tension is 14.7 newtons. And I'll write it over here as well, 14.7 newtons. Okay? So if we look at these, this kind of makes sense. We have an acceleration upward for m1, and the reason that happens is because the tension is greater than the weight. So the tension is overwhelming the weight here, and we're getting an upward acceleration for m1. Okay? Now for m2, we have a weight of 29.6 newtons downward, and a tension of 14.7 newtons upward. So again, the weight is overwhelming the tension, and we're having a downward acceleration for this guy.